In this video, we're going to talk about running a full hypothesis test. Now, we're only doing hypothesis tests where we happen to know sigma, which is the population standard deviation. So in all of our problems, that is going to be given to us. So first, let's go ahead and highlight the steps for the hypothesis test. And we're going to run a couple, and then I'm going to kind of talk about the theory behind it a little bit, just so that it kind of makes sense. So when we run a hypothesis test, the very first thing we want to do is write the null and alternative hypothesis. So we call that H sub 0 and H sub A. Remember, the null hypothesis is always going to have equals. That's how we're going to use it, always with the equal sign. And the alternative might be less than or greater than or possibly not equal to. Okay, now alpha is going to usually be given to us. And you might remember that alpha is the chance that we'll make a type 1 error. If they don't give us alpha, we need to pick alpha based on our concern regarding making a type 1 error. Now, most of the time, alpha tends to be 1%, 5%, or 10%. A safe one to pick, if you're asked to pick, is 5%, and it's pretty standard. Otherwise, they'll usually give it to you and you don't even have to worry about that. Now, the third thing you want to do is find the z-score. Now, this is based on the sample. And we will use the formula for z-score, but we're going to kind of write the formula a little bit different. We're going to use it with the altered standard deviation since we're going to be working with samples. So this is on your formula sheet as well. So do x bar minus mu. Mu, by the way, is the same mu from the null hypothesis. So that's from the null hypothesis. Okay. Divided by sigma over the square root of the sample. All right, so that's the formula I'm going to use. You could just calculate the sigma over the square root of the sample, like this bottom part. You could do the adjusted sigma by itself and then do the z-score. That's fine. But that's what we're doing. I'm just kind of doing it all at once. All right, then we're going to find the p-value. Now, the p-value is the probability of our z-score occurring. In other words, it's the probability that our sample occurs, assuming the population mean from the null hypothesis is correct. So this is going to come from the table. So we will be using the table to get our p-value. And then we're going to compare the p-value to alpha to write our conclusion. And in a previous section, we did state that when the p-value is less than alpha, that's when we're going to reject the null. And believe then that we have enough evidence to support the alternative hypothesis. We will write all that out. So let's go ahead and try an example. And then I'm going to, actually, we'll do a couple examples. And I'm going to kind of, like I said, go a little bit through the theory because there was a third example I probably should have included, but I'm going to talk about the theory so that hopefully helps set you up. All right, so Jeffrey, as an 8-year-old, established a mean time for swimming of 25, for the 25-yard standard deviation. Okay, so we are given his mean and standard deviation. Let me just write that down. His mean is 16.43. Standard deviation is 0.8. Okay. His dad thought he could go faster with some goggles. He bought him a nice pair. He had him swim for 15. So there's our sample, 15 swims. And in that, he got a mean time of 16 seconds. So that is our sample mean. So his dad thinks it helped him go faster. Let's use a hypothesis test to see if that's the case. All right. And they gave us that alpha is 0.05. All right. So we're going to use that. Let's go ahead and write our null hypothesis. So his mean is held to be 16.43, and he believes that is now faster, so smaller than 16.43. Our alpha of 0.05 is chosen for us, so we don't need to select alpha. We can go ahead and calculate the z-score, which would be our x bar minus mu over sigma divided by the square root of our sample size. Now, if you're going to put this all in the calculator, you need to put it all in parentheses, okay? Otherwise, do it in steps. Let's see. I had plugged it in and got 2.08. So that is my z-score. Oh, sorry, negative 2.08. My bad. Negative 2.08. Okay, now that makes sense when I think about the visualization of this null hypothesis. So we briefly talked about this in a previous section, that based on the way the alternative hypothesis is facing, our null hypothesis that kind of has a picture attached to it. In this case, the picture is that because we're thinking that the mean is actually no longer 16.43, but smaller than that, that means that this is what they call a left-tailed test. And I'm basing that on the alternative hypothesis. Okay. So we're going to keep that in mind, and we're going to look up our z-score of negative 0.208. So here, I did pull up my formula sheet. Let's go ahead and grab that and see. Negative 2. Here, I'm going to zoom out just a smidge so I can see more. Negative 2.08. Okay, cool. So negative 2.08. I am seeing 0.01876. So that value right there. Negative, sorry, 0.01876. All right, so let me go write that down. So I got a p-value of 0.01876. Okay, now I'm going to compare this to alpha. Compared to alpha, alpha was 0.05. Yep, 0.05. And this is clearly smaller. So because my p-value is smaller than alpha, what we're saying is that this sample has such a low probability of occurring, about 2% probability of occurring, that's so low, we think it's super unlikely. And therefore, we made a bad assumption. And that bad assumption was the initial null hypothesis. Therefore, we're going to reject the null hypothesis, meaning we believe we have enough evidence to support that the mean swim time has decreased or improved, if you want to use the words they used in the problem. But I'm referring to the alternative hypothesis, the fact that I'm thinking that it's less than 16.43. Okay, so briefly, I want to talk about what this statement here means and why that's the significant conclusion for us. So 0.05 comes from this picture right here. In fact, I kind of drew it intentionally, the same color that I've been drawing alpha in green. That's supposed to be alpha. Our p-value is smaller than that amount. Our p-value is somewhere in here. It's smaller. If I were to have drawn the p-value, it would be a smaller area because it's a smaller area. It's 0.01876, which is smaller than 0.05. So what that is saying is that my sample fell into what they call this critical region. Alpha represents this cutoff point that when we get into the alpha region, we just believe our sample is so ridiculous that we must have made a bad assumption from the null hypothesis. Okay, we'll talk more about that again, but let's go ahead and try another example. So a college football coach, wow, records the mean weight that his players can bench press as 275 with a standard deviation of 55. Okay, so there's our mean, 275, standard deviation of 55. Okay, 3 of his players thought that the mean weight was more, so they think he got it wrong. All right, so they talked to 30 of their teammates, that's our sample, and asked them to estimate um, the amount they can bench press. And then they got the data and they listed it for us, and they used frequencies, meaning how frequently they occur. So given that data, we need to find X bar. That's the piece of information we're missing. Now, I did go to Excel and enter it all in, and I got 286.166666 repeating. Okay. So let's go ahead and come back here. Oops, hopefully you saw that. I just realized that if I don't decrease the page, they may not show you that. There we go. So I got it from Excel. If this didn't show up a second ago, sorry. I went ahead and put all the data, I like literally listed out. See how I have 205, 205, 205 listed 3 times because they said it had a frequency of 3. All right, so 286.167. All right, so let's come back to the notes. 286.1667. I usually, if I have decimals, will at least do 4 decimal places, if not more. Okay. I like to make certain that I've got that correct. Otherwise, I might get my answer a little bit off. So more decimals is a little bit better. Let's go ahead now that we have all the information we need. Let's go ahead and write our null and alternative hypothesis. Okay, so the null hypothesis, that's the 275, and they think it's more than 275. Now, alpha, they chose 2.5%. That is not as common, but it does happen. You don't have to have alpha being 1, 5, and 10. I believe all of the homework use 1, 5, and 10, but it really doesn't matter. We're just going to use that as our alpha. Okay, so let's find our z-score then. So we're going to do 286.1667 minus 275 over 55 over the square root of 30. And by the way, because our sample size is 30, it's normally distributed by the central limit theorem. Okay, so I'm going to enter this in. I didn't have this one ready to go. Minus 275 divided by 55 over the square root of 30. All right, so I'm getting 1.11. And I'm rounding to 2 decimal places because I'm going to use my table. So 1.11. Now let me go ahead and draw my picture really quick because we do have a different picture for this. In this case, since our alternative hypothesis is greater than that value, that means that we're looking at a right-tailed test. So we're actually on the right side this time. So when I look this up off the table, I'm actually going to need to subtract it from 1. So let's look 1.11 off the table here. Oops. Let's see. Okay, so I need to go to the positives. 1.11. Okay, so that is 0.86650. 0.86650, which I'm going to subtract from 1 and get 0.1335. All right, so there is my p-value. Now comparing that to alpha, I'm just going to compare that to the alpha of 2.5. So 0.025. This one's definitely bigger. So we would not reject in this case. So in this case, uh, failed to reject. That's sometimes the language that gets used, or do not reject is another language that gets used. Same idea. Uh, what we're saying is there is not enough evidence to support that the mean weight is bigger than 275. And I'll put pounds since that's the measurement we're working in. So we think that they don't have enough evidence to say that the coach was wrong. All right, now visually, what we're saying is our p-value has a larger area. So remember, this represents alpha, our cutoff area. Once we get into the critical region of alpha, we'll reject the null. But our p-value is bigger than alpha. It's like out over here. It's got a bigger p-value. So it's not in the critical region. In fact, it contains the critical region. It's bigger than the critical region. So we do not reject when that happens. So this kind of graphing procedure is what they use when they use what's called the classical approach to hypothesis testing. Now, the one case I didn't get to show you, and the one thing I wanted to go over is what's called the two-tailed test. Here, let me go ahead and let's just pretend that I have a null hypothesis. I'm just going to fully make this up of 10. And the alternative is that it's different from 10. So not equal to 10. So this is a two-tailed test, which means I literally think of it as possibly being above or below the mean. Oh, shoot. I meant to use the green. Darn it, 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 darn it. Okay, there we go. Let me just redraw that line. Good as new. Okay, so in this case, because it could be above or below, alpha is cut in half because it's being split between two tails. Now, that doesn't mean very much to us, except it is going to make one distinction for a two-tailed test. Let's say we go look up a z-score. Let's just say it's a z-score of negative 2.5. All right, negative 2.5. Great. So let me go to my table, negative 2.5. Going to look that up. I don't know why I struggled so hard to decide that. Negative 2.5. Okay, so that is this number right here. So 0.00621. 0.000621. Okay, but that is not going to be the p-value we're going to compare, because that's the p-value for one tail. Happens to be the left tail because our data gave us a -1. What we actually have to do is multiply the p-value by 2 because this thing is two tails. So our p-value is actually going to be 0.00621 times 2, 0.01242. And that is the p-value that we would compare with alpha. And let's just say I said alpha is 0.05 because I'm making this problem up. So why not? What's wrong with 0.05? Nothing's wrong with 0.05, which would happen to be bigger than my p-value. So I would reject in this case. I would reject the null in this pretend example that I've made up without any sort of problem. So the key step is when you are doing a two-tailed test, you need to multiply the p-value by 2 and then compare it to alpha, because the p-value is being considered for both of these tails. And that is the only thing you need to know then, going ahead and trying the homework.